I welcome you all in this video. In this video, I am going to explain you the permissible stresses or allowable stresses. How to find out these permissible stresses or allowable stresses, on which factor this permissible stresses depends, and which are the types of permissible stresses that we are going to discuss. So before that, you might have studied this factor of safety concept, FS. So FS is the ratio of failure stress to the allowable stress or permissible stress. So failure stress is also called as maximum stress, and this allowable stress or permissible stress is also called as design stress or working stress. Now this permissible stress we can find out from this ratio. Just take this permissible stress or allowable stress on the LHS. Now I will use only one term out of these two terms, so I will write here permissible stress. So permissible stress on the LHS, Fs will be in the denominator, so failure stress upon Fs becomes permissible stress. So from this equation we can calculate the permissible stresses. Now remember that the types of permissible stresses. The permissible stresses types are depending on the loading condition. If the loading is of tensile nature, that is, if the component is subjected to tensile stress, we must consider permissible tensile stress. If the component is subjected to compressive stress, we must calculate permissible compressive stress. So likewise, we have to calculate the permissible shear stress, permissible bending stress, and permissible crushing stress. Okay, so these are the types of permissible stresses, and that depends on the loading condition. Now next is FS. General guidelines are provided for selection of the value of factor of safety. So these general guidelines are: for ductile material its value must be 1.5 to 2, and for brittle material its value must be 3 to 5. If you look at these two values, for brittle material this value of factor of safety is higher, because we know that the failure of brittle material takes place suddenly. It will not show any signal. That means the brittle material will not deform before the failure, so it is very difficult to predict the failure of brittle material. It is very difficult to identify the failure of brittle material. So the more safety is needed in case of components made up of brittle material, because it does not deform before the failure, and hence the factor of safety is more for the brittle material as compared to ductile material. Now these are just guidelines given for the designers, but you can change these values depending on the factor depending on the safety required. For example, if you consider the bearing, if you want to design the bearing for simple machine, okay, which is used for just simple machining operation, and similar consider if you want to design the bearing for aeroplane. Now while designing the bearing of machine, you don't need more factor of safety, because if the bearing of machine fails, which is used for general machining, you just need to replace that bearing, so it will require just maintenance time and maintenance cost. But if the bearing of aeroplane fails, it will cause the hazardous situation for the human. Okay, it will create the threat to the human life. So in such cases, the bearing in the machine should be provided relatively less factor of safety, and the bearing of aeroplane must be provided higher factor of safety. So that depending on such factors, we have to select the factor of safety. So these are just guidelines. Now we have seen that the value of Fs, so these are the values of Fs, general guidelines. Now we'll see failure stresses. What are the failure stresses? Now failure stresses are those stresses at which the component fails. So failure stresses are those stress at that stress the component fails. So we have to see for a ductile material. So first of all, we'll write here failure stresses. Okay. So failure stresses for ductile material. First of all, we'll write failure stresses for ductile material. Now why you are making this category for failure stresses, that is separately for ductile material and separately for brittle material? Because the failure stresses for ductile material are different and failure stresses for brittle material are different, because both material have different characteristics. Ductile material, before failure it deform permanently, but brittle material does not deform before the failure. So failure stresses for ductile material are different and for brittle material are different. So just for the your understanding, I will again go through this stress strain curve. So we know that this is the stress strain curve for ductile material and this is the stress strain curve for a brittle material. Now we know that what happens at different points. this is the specimen of tension test, and we know that what happens to this simple tension test specimen at different stresses. Now we know that up to elastic limit, this specimen, which is made up of ductile material, deforms elastically. That means when this load is removed, specimen can regain its original shape and size. But when the stress in this specimen made up of ductile material reaches the yield stress, that is SYT, this specimen deforms permanently. That means at stress, when the induced stress in this specimen reaches the value of SYT, that is yield stress, this specimen deforms permanently, and that is the one type of failure. Permanent deformation is the first type of failure that occurs in the ductile material. So at yield stress, first type of failure occurs, that is called as permanent deformation. Now if you increase further load in the specimen, the stress increases in the specimen, and it will reach to its maximum stress. Beyond that, you cannot increase the load. So it reaches the maximum stress in the specimen, and that stress is called as ultimate stress, that is SUT. When the induced stress in the specimen reaches the ultimate stress, that is SUT, the neck is formed in the specimen, the neck is formed in the component, and beyond this ultimate stress, if the specimen or component is stressed, it will directly get fractured out. So this means that there are two types of failures occur in the ductile material. First is permanent deformation, and then neck formation and permanent breakage. So in the ductile material, first failure occurs as permanent deformation. So we have to consider failure stress for ductile material as SYT. Okay, but here specimen is subjected to tensile stress, so we have to consider failure stress for ductile material as SYT, that is yield strength in tension. If specimen is subjected to compressive stress, then we have to consider yield strength in compression. If specimen is subjected to shear stress, we have to consider the yield strength in shear. So likewise, we have to change the failure stresses for ductile material, but these are related to SYT. Now consider the stress strain curve for brittle material. Now in case of brittle material, there is no yield point, because brittle material does not deform before the failure. So as we increase the stress, the strain increases, and at certain limit, at certain point, at certain situation, the maximum stress condition is reached. Beyond that, you cannot load this specimen. You cannot increase the stress. If you increase the stress beyond this ultimate stress, that specimen directly break without showing deformation, without deforming, that component directly break. So this is the failure stress for brittle material. So we can say that SUT is the failure stress for brittle material. That means beyond this stress, you cannot load the component. You cannot increase the stress beyond this SUT. So for brittle material, SUT is the failure stress. And for ductile material, failure stress is SYT, because first type of failure occurs is the permanent deformation. So we have to design the components made up of ductile material first to avoid the permanent deformation. And here, in order to design the components made up of brittle material, we have to take this SUT as a failure stress.